Welcome back to this video series of simulating a supersonic rocket with Ansys Fluent. In this video, part 5, we'll follow the solution process, assess convergence, and post-process the results with both numerical quantities and results visualizations. With the solution initialized and the Mach number contour shown for reference, we'll start the simulation by defining the number of iterations to take. We'll start with 250, as this solution should converge within 180 iterations. If the simulation has previously been solved, you'll be prompted that the monitor files will be overwritten. Acknowledging this dialog box allows the solver to start. Upon starting, windows are populated with the residuals, monitor plots, and any other defined solution objects. As the simulation progresses, we'll watch the residuals to ensure that they start to curl down, as well as check that the monitor values start to level off. Decreasing residuals indicate progression towards a steady-state solution as the difference between each iteration is reduced. Once all residuals reach their specified limit, the simulation will be complete. To check convergence, we can see all residuals are below 1e-3 and that the report monitors are invariant. Another important check for convergence is the conservation of mass and energy. To do this, we'll calculate the mass flow rate of all the inlets and outlets and divide the net flow rate by the outlet flow rate. This gives the mass imbalance of the entire domain of 0.2%. And I'll do the same for the total heat transfer rate in and out of the domain, which gives a similar conservation of energy of 0.2% for the simulation. Checking the Mach number contours, we have a nice, realistic solution. However, if your residuals are not dropping, the simulation is not converging, or the flight speed is greater than Mach 2, then the pressure-based solver might be inadequate to achieve a solution. In this case, the density-based solver with FMG initialization can be used. This is a powerful initialization method used only with the density-based solver. It provides a better initial guess for the flow field, especially with high-speed flows. It can reduce the number of iterations needed for the solver to converge, though the density-based solver generally has longer solve times, and thus the pressure-based algorithm is preferred where applicable. Inspecting the initial solution with FMG, we can see a much more realistic starting point compared to the hybrid method. Returning back to our original converged solution, we can visualize the solution by inspecting the contour plane that we created before. The contours of Mach number show the velocity variations in the flow field, with abrupt changes in the constant Mach 2 flow field and jet exhaust representing shock structures. A shock can also be seen coming off the nose of the rocket. To improve this visual, we'll add a mesh object to view the rocket body surfaces, ensuring that faces are selected to be displayed. We can then combine these objects in a scene to better see where on the rocket body the shocks attach, and observe a shock originating directly in front of the fin and the wake behind the fin. Finally, we can improve the depiction of shocks by selecting the contour lines option in the Mach field display, with significant shock boundaries defined by the contour lines. To probe specific regions for quantitative results, double-click with the right mouse button, and the solution field value will be printed in the console, showing the max and min of the probe range. Here, we see the bulk free stream flow is Mach 2. The shock emanating from the fin is the result of an abrupt velocity change to Mach 1.9. The wake region outside the jet and behind the fin is subsonic, and the jet exhaust exceeds Mach 4. To see the solution field of other variables, simply make another contour graphic with the variable of interest. Here, we'll choose velocity magnitude, and again, the midplane for display. With all graphic objects, you can modify the color map for better visibility, and also add the new object to your existing scene. Another variable of interest is the static pressure. We can include both pressure and Mach number contours in our scene to see that the regions of low pressure align with the location of shocks, as there is an abrupt change in pressure value where shocks occur. The location and strength of these shocks is important in predicting the drag of the rocket. The calculated value for drag of the rocket can be found in the force reports under the Results tab. Selecting all the exterior walls and aligning the direction vector with the flow provides the results for the pressure drag, viscous drag, and total drag for each part of the rocket, which gives the total drag force. However, the drag coefficient values are not real numbers. To fix this, we must ensure that the drag calculation is using the correct free stream velocity and density values by setting the reference values to be computed from the free stream inlet. The calculation now gives a correct drag force of 316 newtons on the rocket body and a corresponding drag coefficient of 0.0014. As we are simulating only a quarter of the rocket, the total drag force acting on the entire rocket must be multiplied by 4 to determine a net drag force of 1,267 newtons. The force reporting is also used to find the center of pressure. As the rocket is symmetric radially about x and y, we are only concerned with the z coordinate. The center of pressure location can be visualized by creating a point with the z coordinate displayed. For the operating conditions in this simulation, the center of pressure is located at the very end of the rocket. This location is well behind the center of mass and will result in a stable flight. However, being located behind the body indicates overstability and excessive drag. Now assessing the solution accuracy, we see that viscous drag makes up a significant portion of the total drag force. When using the K-omega SST turbulence model, the accuracy of viscous drag forces depends on the resolution of wall effects. This is indicated by the Y+ value. Looking at the Y+ contours on wall surfaces show that the majority of walls have a Y+ between 30 and 300. Zooming in, we can see the Y+ value changes in alignment with the BOI sizing regions, as Y+ is a function of the first cell height. For drag predictions, wall models will give a reduced accuracy for Y+ between 30 and 300. To improve drag predictions, the model must be remeshed with a smaller first layer height, giving Y+ less than 5. Next, to check the flow field resolution, we can add the cell outline to our graphics scene. Here, we see the boundary layer cell's height increase where BOIs change, as well as some smearing in the shock structures of the exhaust velocity solution. To improve resolution, cell adaptation can be utilized under the Domain tab. Selecting Manual Adaptation and the Mach Hessian criteria will refine and coarsen the mesh structure where it exceeds gradient limits. These gradients can be set manually, but we'll just use the defaults. Selecting Display will show the regions to be refined, as there is a large number of cells this might take a moment to display. Then, pressing Adapt will perform the refinement and show the new mesh size. Care should be taken with mesh adaptation, as we can see the cell count has nearly doubled. Displaying the mesh scene again, we can see the refined regions where there is increased cell count. Specifically, these are regions with a high Mach number gradient, such as shocks and the jet exhaust. Finally, we'll rerun the simulation to calculate the refined solution. The residuals and monitor values will change abruptly before slowly converging again. Note, this simulation was run on 32 processors due to the increased mesh size. As the solution progresses, we observe the change in monitor values and the reducing residuals. The calculation finishes as residuals have reached their specified limit, however the velocity monitor is not converged. You could reduce the residual limits and continue running the simulation, but for this example, we'll just inspect the refined velocity contours. Zooming in, we can see better defined shocks and a clearer exhaust plume structure. To continue improving resolution, you could do iterative cell adaptation. However, the accuracy must be balanced with computational efficiency as the mesh continues to grow with every adaptation iteration. And this concludes this video, as we investigated the solving process, results extraction, and solution refinement. In the next and final video, we'll show how to combine the geometry, meshing, and solver components with Workbench to run a full parametric study for rocket design.